Welcome. I hope you guys are enjoying reInvent so far. Thanks for joining our talk. This is CMP314, and today we're going to talk about bringing deep learning to the cloud with SIGOPT. My name is Tom Jones. I'm a solution architect for AWS on our partner team, and I've been at AWS for about 4.5 years now. Joining me on my talk today is Scott Clark from SIGOPT. Scott is the founder and CEO of SIGOPT, which is, I don't know if anybody saw the announcements this morning about our machine learning competency that we just launched. SIGOPT is one of our launch partners for that, so thank you. And before Scott talks, I want to lay a little foundation on AWS and machine learning, just to give you a little bit of background. So why do we have this hype around machine learning today? Well, there's 3 factors. First, data is abundant, right? Machine learning needs a lot of data, and we have that today thanks to inexpensive storage through things like services like S3. And companies are realizing that data has value, so they're saving it and saving it all. We also see advances in algorithms. So things like backpropagation and dropout algorithms are really advancing the utilization of machine learning. And then last but not least is horsepower. So in order to process all that data, you need a lot of compute. So it's accessibility and affordability of compute as a third vector that's driving machine learning today. Okay, well, why is that important? What is machine learning used for? Or what are people doing with machine learning? Well, there were 2 initial areas where machine learning excelled, and that is language processing and computer vision. But recently, what we've been seeing are a couple new areas that are gaining a lot of traction around time series analysis and reinforcement learning. Reinforcement learning is great for robotics and learning motions, and time series analysis is great for things like IoT data. But all of these are, if we look at this from a high level, all these are really ways to do pattern recognition. So here's some examples of pattern recognition. Looking at images, finding scenes, facial attributes, persons, or even objects inside of images. So for all of those folks in the audience who are fans of Silicon Valley, it's hot dog, not hot dog, right? We've got data, right? Data patterns, looking at optimization, anomaly detection, reinforcement learning inside of data. And then language, so we've got processing, character recognition, and translation. So these are all ways that machine learning is being used today with pattern recognition. So at the end, or in summary, machine learning finds patterns in data, and it uses them to make predictions. So you can take your data, combine it with machine learning, and build intelligent applications. So how does AWS help? So AWS has a number of services, starting with our infrastructure services, that can be applied. So I mentioned horsepower and compute earlier. So we have our Amazon EC2, that's Elastic Compute Cloud instances, with CPUs, with GPUs, and now with FPGAs. All of those are ways that you can utilize compute to accelerate machine learning workloads. We also have services like AWS IoT and AWS Mobile, as well as supporting all the major frameworks for machine learning, like Apache MXNet, TensorFlow, and Caffe. Our platform has services in it as well, so Amazon Machine Learning, Amazon EMR, which is Elastic MapReduce, AWS Batch, and the AWS Deep Learning AMI, So the deep learning AMI is a pre-configured AMI where we've installed all of these frameworks for you. All you have to do is launch it, and you can start to be productive with any of those frameworks today. And then last but not least, our managed services. So Amazon Rekognition for image analysis, Amazon Poly and Lex for text-to-speech and speech-to-text. And I'm hopeful that we'll see some more things this week that will add to this list. So to talk about compute for a second, so AWS has a broad set of compute types that you can utilize for your different workloads, from general purpose instances like the T2 and the M4, to compute optimized instances like our C family, to storage and I/O optimized instances, memory optimized instances, and our GPU and FPGA enabled instances. I want to deep dive for just a minute on our C5, the F1, and the P2, or P3. We can talk about P2 too, but the P3 is the latest. Okay, so the C5 is our newest generation of compute-optimized instances, and it provides an Intel or a Skylake-based Intel processor running at 3 gigahertz with a turbo boost up to 3.5 gigahertz. It is offered in these various configurations that you see here, up to 36 cores, which is 72 vCPUs, 144 gigabytes of memory. It offers up to 25 gigabytes of network performance through our Elastic Network Adapter, or ENA. It has NVMe-based EBS, that's our Elastic Block Storage, and it supports AVX 512 extensions. So the Amazon F1 is a compute instance that has field programmable gate arrays, or FPGAs, attached to it. And you can program the FPGAs to create custom hardware acceleration for your applications. These F1 instances are offered in 2 different instance sizes that include up to 8 FPGAs per instance. F1 instances include 16 nanometer Xilinx UltraScale Plus FPGAs, and each FPGA includes 64 gigabytes of DDR4 EEC protected memory with a dedicated PCIe 16x connection. Each FPGA contains approximately 2.5 million logic elements and approximately 6,800 DSP engines, or digital signal processing. Just like all of the other Amazon EC2 instances, the F1 is available by the hour, on demand, with no long-term commitments and no upfront payments. There we go. Click. I did click that. The Amazon, and last but not least, the Amazon EC2 P3 instance type. So the P3 instances are a next generation EC2 compute optimized GPU-based instances. So these are powered by up to 8 of the latest generation NVIDIA Tesla V100 GPUs. And they're ideal for computationally intensive applications, such as machine learning. They leverage up to 64 vCPUs using custom Intel Xeon E5 processors, up to 488 gigabytes of RAM, and up to 25 gigabytes of networking, just like we saw with the C5s using the ENA. So it's based on NVIDIA's latest Volta architecture, and each Tesla V100 CPU or GPU provides up to 125 teraflops of mixed precision performance. And so that's kind of the background of AWS and machine learning. I want to hand it over to Scott and have him tell you a little bit about SIGOPT. Scott?
Thank you, Elvis. Hello, everybody. So I'm going to tell you a little bit about SIGOPT and how we leverage AWS to enable our customers to really unlock deep learning and AI, and how we've built upon all of the different services that they provide to build our own internal infrastructure, but then also leverage theirs as well. So SIGOPT is a small startup in San Francisco. We were just recently announced and are honored to be a part of the AI competency that was announced this morning at the keynote. And I'm going to walk you through exactly what we do, how we do it, and why you should care about it. But first up, I'm going to start with 2 axioms. 2 things you may already know, but are the basis of this talk. So the first is AI and deep learning is super powerful. We're at this really unique moment in time where all the pieces are kind of coming into place. People have had data for a long time. Sometimes they've been collecting it for decades. But there wasn't always the infrastructure in place to be able to really leverage some of the most sophisticated algorithms. But now that's available today. And Elvis talked about some of the great infrastructure you can leverage using EC2. But on top of that, now we have the frameworks in place too. With open source contributions like MXNET and TensorFlow, it's been easier than ever to be able to get up and running with some of these very sophisticated techniques right out of the gate. No longer do you have to go and compile and kind of code up 100 different research papers in order to get started with some of these techniques. It's just spin up a deep learning AMI, you have a GPU at your disposal, pipe your data in, and you're off to the races. But there's this new bottleneck that this has opened up, and that is tuning these systems and getting the peak performance out of them is still incredibly non-intuitive. It's very time-consuming and expensive, and it can mean the difference between getting peak results or results that underperform maybe a less sophisticated method. And this is exactly what SIGOPT is set out to help solve. Basically, we take your machine learning, deep learning, reinforcement learning algorithms and help tune all the different configuration parameters that go into them. These are the hyperparameters, architecture parameters, things like learning rates and number of hidden layers that you need to set before you even start training. So the goal is to get to the best configuration as quickly, efficiently, and as well as possible. And the reason why this is a problem is literally every single machine learning and AI problem has these tunable configuration parameters. From the simplest random forest, where you need to select the number of trees, to k-means clustering, where the hyperparameter is in the name itself, all the way to deep learning. So what this is an example of TensorFlow. So this is a website you can go to right now, playground.tensorflow.org, and basically tune a neural network in your browser. And when you look at this, you should be thinking about 2 different things. One is, what problem are we trying to solve? So on the right here, we have a bunch of data, orange dots and blue dots. They're in this kind of Swiss roll spiral pattern. And we want to be able to come up with a surface that differentiates between the blue dots and the orange dots. So imagine you're doing fraud detection. Every single orange dot is a fraudulent transaction, and a blue dot is a good transaction. So we want to be able to flag the fraudulent ones and not the blue ones. Every time we harass a customer, that costs us a bunch of goodwill. Every time we miss fraud, it costs us a bunch of money. So how do we leverage AI to do this? Well, we can throw a neural network at it. But the problem is we need to set all these configuration settings. So by bolting SIGOPT on top of this system, what we're able to do is rapidly test different configurations. Try different architectures, try different hyperparameters. And as we learn about how that system is responding to these different configurations, we can drive you to better and better peak performance until eventually you get to this network architecture here, which is still relatively shallow, but gets you much better results than that default performance. And so this only gets trickier and trickier as you really dive into these systems, because more often than not, you're not playing with a graphical user interface. You're looking at code. And in that code, sometimes buried deep within that code, is a bunch of magic numbers. So this is the RMS prop optimizer within MXNET. So this governs the stochastic gradient descent that actually learns the weights of the neural network. And as you can see here, there's some keyword arguments. Learning rates, gamma 1, gamma 2. And it's a relatively opaque interface. How do you decide what's the best configuration that maximizes your accuracy of your fraud detection model? Well, we can look a little bit deeper into the docs, and we can see, well, gamma 1 is, of course, the decay factor of a moving average for gradient squared. So should it be higher or lower if you have more data? What even is the range of this parameter? How do we go about setting this? And that's why a lot of times this is a very trial and error-based proposition. It feels like you're climbing a mountain in the fog. And worst case, this isn't the type of trial and error that's very easy to just brush under the rug, because it's extremely time-consuming and expensive every single time you want to try something new. So if you have to pipe in all of your data and spin up some of these powerful deep learning instances that Elvis talked about, it's still very expensive to kind of try a specific configuration. So imagine you're trying to climb a mountain, and I gave you a specific long, so latitude and longitude, and you're trying to find the highest possible altitude. So you go to that position and you measure your altitude, then I give you another one and you have to go there and do it again, and it's very expensive to do so. It could be even more expensive to try to tune your fraud detection algorithm. It could take days on a cluster. And unfortunately, the standard methods people have been using to attack this problem for the last few decades just don't scale in this time-consuming and expensive space. So typically, people will have these AI models already in place. They have these parameter configurations, these weights, these thresholds, these hyperparameters, architecture parameters, et cetera. And 90% of the time when we go and talk to a customer, they're doing one of three things. They're either doing an exhaustive grid search. This is the brute force approach to that problem. It's literally lay down a grid of all possible options and try everything. That could work if you're tuning one or two parameters, but it scales exponentially with the number of things that you're tuning and tweaking. So this is like trying to climb that mountain by literally stepping on every single grid point of a long map, and then at the very end saying, what was my highest altitude? That's not how you would go about doing this process. Random search is another very popular method. In fact, there's this great paper from NIPS, one of the premier machine learning conferences in 2012, saying that this is actually far superior to grid search. Just try random solutions. This is like trying to jump out of an airplane and hoping you land at the peak of that mountain, and then just doing that over and over and over again. Unfortunately, this requires you to be lucky, that you will kind of randomly get into a good configuration. And luck is not a great business strategy, and it's also an extremely inefficient optimization method. So some people say, well, we're not going to use these because obviously they take too much time and effort, so I'm just going to manually tune and tweak this. But humans are really, really bad at doing high-dimensional optimization in their head. I don't think anyone in this audience could reliably do 15-dimensional optimization via trial and error and get to any sort of globally good solution. But unfortunately, a lot of people do that today. There's, of course, more advanced methods that have been around for a long time in optimization, things like genetic algorithms, particle or population-based methods, simulated annealing, things like that. But they typically assume that it's cheap to evaluate the underlying function, and so you can evolve a strategy slowly over time. But we're assuming it's expensive here. So, Bayesian optimization to the rescue. What this does is it treats the underlying system like a black box. We can sample specific configurations, learn how well they performed, and then leverage that to decide what to do next. So what SIGOP does is provide that suggestion. The customer then returns how well it performed. So if we're doing fraud detection, that would be maybe an accuracy or an F1 score. If we're tuning an algorithmic trading strategy, it might be a Sharpe ratio. It could be some sort of expected revenue in a recommendation algorithm. Whatever it is that correlates with business value, that's what we're going to try to drive up. So we learn from how these individual configurations have performed to suggest new ones and slowly, or actually rapidly, converge you into better results. And the idea here is, once again, this is what's called black box optimization. So the Bayesian optimization method has no idea what's actually underneath the hood. All it knows is this configuration went in and some value came out. In the same way that your algorithm doesn't know what's underneath our hood, although I will show you a little bit here in a minute, but you just get a configuration and then you tell it how well it did and then repeat. And the core kind of intuition behind this is this trade-off between exploration and exploitation. So back to grid search and random search, they're just kind of blindly sampling things. But what we're doing is we're exploring how different configurations have performed, learning about that underlying system that we're optimizing, and then exploiting that information to then get you to higher and higher results. So we're learning the general surface and then exploiting local optima in order to get you to better results and kind of constantly trading that off to be an efficient global optimizer. So what's actually in that black box? How do we build it? How do we leverage AWS to do it? And how do we serve it to our customers? So there's the actual optimization framework itself. And then there's also an evaluation framework that we use to test how well our algorithms are actually performing to make sure that we can reliably, accurately claim that we're the best in the world at this. So first, I'm going to walk you through that optimization framework. We've built this on top of AWS from day one. It's been incredibly helpful in taking a small idea, my PhD thesis all grown up, and quickly leveraging it and deploying it around the world. So there's a couple of different ways that customers can interact with us, and I'll walk through that slide here in a second. All of this will be available online as well. I see some of you taking pictures. So first, a customer can come to us via the web interface. This gives them access to our advanced analytics dashboard, so they can really see how we're optimizing, which parameters are important, making sure that we're converging to that ultimately best solution. They can also directly hit our API, either from the web interface or via our REST interface. This then spins out into our API cluster, which can handle each of these individual requests in a very asynchronous fashion. Once you hit the API, you can either go over into one of the services that we've built up. Each one of these, again, is kind of a Russian doll of nested load balancers and EC2 instances, or hit the optimizers themselves. And these are the really compute-intensive parts of SIGOP that leverage some of the technologies that Elvis was talking about. It's extremely computationally intensive to build up this ensemble of Bayesian optimization techniques that powers our engine. Additionally, there's more complication throughout. Obviously, these architecture diagrams can be infinitely complicated. Every API instance can do more than one thing. They can be talking to individual services. They can be talking to optimizers. These optimizers can elastically scale up and down as our customer needs demand them. And the entire thing is parallelizable kind of on multiple levels. And this is something that we wouldn't have been able to do ourselves, to be completely honest. If we had to devote the resources to building the actual physical servers and slowly scaling them up, it wouldn't have allowed us to move as quickly as we've been able to and service our customers. On top of this, being able to deploy within AWS has allowed us to do some other very clever and fun things. So traditionally, when you're doing optimization, you may think of this as a serial endeavor. I give you one thing to try, you tell me how well it did, and then we repeat. But you can actually leverage the partial information you get from knowing, OK, I know I'm going to get a response back about the specific configuration. Maybe I want to try a second one as well. And some of these deep learning architectures are incredibly great at scaling within a single machine, but it can be very difficult to scale them across multiple machines. So what you really want to be able to do is have a single point that can handle the distributed scheduling of all of these jobs, and not have you have to write your own wrapper on top of TensorFlow or whatever it may be to build up kind of a scalable cluster. And so SIGOP enables this by being that kind of scheduler of hyperparameter tasks. And it does this without you needing to have any information between these individual deployments. So that could be one instance of TensorFlow running on a bunch of GPUs in US West 1, and a bunch of them running on C5 instances in US East 1. And all you need to be able to do is communicate over the internet to SIGOP. And what was also announced today in one of the other keynotes was you can also do this with a virtual private endpoint using Private Link within your AWS VPC as well. So it doesn't even need to go over the open internet. But SIGOP acts as this distributed scheduler. You fire off your tuning, go get a beer, and check the results on your phone. So I just told you that I have this magical black box that'll help you tune all of your functions. How do you know I'm telling the truth? Well, how do we know we're even telling the truth? How do we know that we're actually making progress? To answer these questions, we've built up an evaluation framework within SIGOP. So what do we actually needed to do? We needed to be able to tell us how well the optimizer is actually working and how well different improvements to it are actually making a difference. So we publish and present at a lot of the top machine learning conferences in the world. Bayesian optimizations become very popular at ICML and NIPS and AI Stats and some of these great places. But it's often hard to tell what looks like a good theorem and what actually makes a big difference in practice. And so we need to be able to do that as rapidly as possible so we can continue to iterate and compare against other methods. This is based on 2 papers that we presented at ICML in 2016 around this evaluation system and then a robust comparison method. So when you're comparing 2 optimization strategies, what do you even care about? Well, one is you want the best possible optimizer, the one that gets you to the highest possible result. The definition of optimization is taking something and making it better. So if I have a red optimizer here and a blue optimizer, which one got to a better accuracy of my fraud detection method in the fewest number of steps or in some fixed number of steps? You might also want a fast optimizer. So who got there quicker? If there were a tie for who was the best, in this case, red was able to get there significantly faster than the blue method. You also want a strong optimizer, one that's robust, one that you can go to time and time again for different problems and be able to make sure that you get reliably good results. So underneath all of this is the stochastic optimization method. It's trying different things, building up this ensemble of Bayesian optimization techniques and saying, this is what you should be utilizing your resources on. But in the same way as random search, it can give you different results each time. So you need to make sure that you can consistently outperform these other methods. So now that we have these metrics that we can actually use to compare optimizers, we want to throw it at a bunch of different things to see maybe is optimizer A better than optimizer B. So traditionally in academia, the way that you would do this, and I'm guilty of doing this in my PhD, is you pick your favorite functions and you show that you can do better than someone else on your favorite functions. This is the Frankie function here. One of my favorites from grad school is the Brannon function. Unfortunately, what this ends up doing is forcing you to kind of overfit to your favorite little class. So what we did within SIGOPT is we took the superset of all these functions from the academic literature, all of the different kind of pathologically difficult things to optimize. We took a bunch of functions that look similar to our customers' data. We took a bunch of functions that just are using general purpose machine learning frameworks, and we put them all together. And this gets you hundreds or thousands of different kind of hard problems that you would hope a good general purpose optimizer would be able to perform well on. Okay, so now we have some metrics and we have a bunch of hard problems. Now we need to do a bunch of optimization. And this is where we go back to AWS and say, okay, how do we build a scalable and cost-effective way to do this? And that's this evaluation framework that we've built up. It's somewhat similar to our actual optimization framework that's running in production for our customers with some key differences. One is there's no real web interface. The research engineers have to just play with the command line and this kind of interactive browser that we've built. The other thing is a lot of these EC2 instances can be spot instances. Things can die and be spun back up to save on cost. But at the end of the day, we're able to very rapidly do a large number of optimizations. And that is key, because historically, this was a very time-consuming task. This used to be just a bunch of unit tests back when we started SIGOPT in 2014, where, okay, did we do well on this function? Did it break or something like that? And in order to be able to build this up across this wide swath of difficult problems and be able to consistently say that we're doing a very good job, we were able to build the evaluation framework, but we needed to speed it up. So with AWS, we were able to get more than 100x improvement over that localized solution, taking over 20,000 independent optimizations from taking days to run, something that we could only kind of do a regression test every week, to now be 30 minutes. And what this unlocks for our team cannot be understated. Now a research engineer can read a paper, implement it, and then be able to very rapidly say, did this make a difference or not? And then if it did, continue on. If it didn't, throw it out. And so we're able to make measurable, incremental changes and really make sure that this ensemble is constantly getting better, as well as running nightly regression tests to make sure that we never have introduced any sort of issues. And making it iterative, making it 30 minutes, making it interactive has completely changed the way that our research team does the research and implements these incredible new achievements in the field. This also allows us to do a very robust comparison against alternative methods, whether it's the kind of more simplistic random search and grid search, or a particle-based method, population-based method, other open source techniques. At this point, we've tested dozens of other open source approaches to this, including the ones that I've written or other research engineers in our team have written in the past, to really make sure that this ensemble can reliably and efficiently kind of outperform them, both in accuracy and speed and robustness. So, how about a real life example here? So this is something that we did with AWS. It's posted on their AI blog. If you just type in AWS SIGOPT, it'll be probably the first result. And all of the code is available on GitHub, and there's an AMI, so you can actually reproduce this yourself. But this is a fully tuned system where you can kind of interchange whatever it is that you want. So first, once again, black box optimization. We're going to take a machine learning model. We're going to bolt a Bayesian optimizer on top, and we're going to use it to get better and better results. So what's the actual machine learning problem we're going to solve? Well, we're going to take a natural language processing task. We're going to take a bunch of movie reviews from Rotten Tomatoes and basically try to classify sentiment. So this movie was great, positive sentiment. This movie was terrible, negative sentiment, and then things in between where people just kind of tell stories about their lives. And we want to be able to say very rapidly and very reliably whether or not it was positive or not without looking at the reviews. And this can be important for recommendation systems. Before starting SIGOPT, I worked at Yelp for many years. This was very important for kind of understanding the true nature of reviews. But this is kind of a common text processing problem. But the trick is you can leverage very advanced techniques like MXNET, but tuning those hyperparameters and feature transformations and architecture parameters is still this dark art. So what happens when you bolt an optimizer on top of it? And that's what the blog post shows. And how does that compare to other optimizers? So there were a couple of cool results here. One was there's a surprising number of these underlying parameters in these systems. I think we tuned about a dozen in this specific blog post, but you can kind of parameterize all different aspects of the stack. The data that's coming in, how do you transform it, how many words do you look at a time? This only gets more complicated for time series and vision problems. How do you tune the optimizers within the deep learning system itself, et cetera, et cetera. Another cool result is when you are going and doing deep learning, there's a couple of best practices or things that you can do. One is leveraging the best computational resources. Another is having the best hyperparameter optimization. And when you take these two individual things and put them together, it's not an additive improvement, but it's a multiplicative improvement. So in this example, we took an AWS instance with a CPU, and it was using random search, which is the best of the three standard techniques to tune the underlying system. And we compared it to a GPU instance. This was a P2 at the time, but the P3s will only get you better results, and SIGOPT. And so with this, we were able to get a 50x improvement by going to the GPU and a 10x improvement by going to SIGOPT. On average, it was about a 400x speed up across many different tasks between that kind of standard approach. What this means for you is 400 times less wall clock time to get to a specific result. Or just the SIGOPT component, 10x less resources required to get to a better result. And this can be very significant on your AWS bill. And less trial and error also leads you to just better AI, better results at the end of the day. This table shows how many different evaluations were required to get to specific accuracy boosts for this specific problem. What's worth noting here is that grid search, the bottom right part of this table, gets really big really quickly. It's sometimes hard to internalize the exponential function until you have to pay an AWS bill that has an exponential function in it, but it can get very expensive very quickly. Random search, a little bit cheaper, but once again, less efficient, 10 times less efficient than these Bayesian optimization techniques. Also getting worse results. And once again, you want to be able to do this as reliably as possible. So with a tool like SIGOPT, you can take the system that you've built and be able to say, how do I make sure that I'm always getting to the best results? And some of these examples kind of extend on beyond these natural language processing tasks to computer vision tasks, to algorithmic trading, to whatever it is that you're actually building. SIGOPT does this with a kind of advanced analytics dashboard as well, as I mentioned before. This is traditionally kind of the dark art of deep learning. One of our customers had an engineer, and his job was to tune all of the different architectures and hyperparameters of their deep learning systems. And this was a startup. There were only 6 people in this startup. And so this was a big resource to be able to say, I'm going to take 1/6 of the company, and they're going to be the person who does this. And he was selected for doing this because he was the best at it. Because in his PhD, he spent 6 months fine-tuning all the different algorithms in his PhD to get to a specific result. And then SIGOPT came along, and they were like, OK, this might be a way for us to maybe augment this person's workflow. Maybe it'll do OK or like help guide it as well. And what we were able to show was we were able to outperform that human doing that task and get to better results with fewer evaluations, but also free him up to then do what a real data scientist is great at, which is coming up with new algorithms, coming up with new data transformations, new features and things like that, and really apply the creativity and domain expertise required to make breakthroughs that only a human can do. In fact, he was able to take his PhD thesis that once again took 6 months, and he put SIGOPT on top of it, and we were able to actually beat that result over a weekend. And so what this does is it just unlocks all this locked up human potential within these organizations, but it also unlocks that potential within the algorithms themselves. So it's very easy to deploy on top of things like Python, Java, R. Once again, it's just a REST API. All the client libraries are available on the respective tools. Integrates seamlessly with all the frameworks that you know and love, both deep learning and traditional machine learning. And also comes with a lot of features that you wouldn't expect from something like just random search or kind of build it your own open source. Fun things around multi-metric optimization. This is saying, I don't just want to optimize one thing. I want to optimize many things or competing things. So you can always kind of composite metrics together to be able to say, I want to make these specific trade-offs, like an AUC or F1 score that trades off precision and recall. But maybe in the algorithmic trading space, you want to get the most money with the least risk. And how do you kind of understand what's even feasible with your underlying algorithms? And SIGOPT's able to kind of flush out all the potential Pareto optimal or the best possible trade-offs of these multiple metrics. We're able to come up with multiple good solutions, kind of a portfolio of local optima. This allows you to be able to say, once again, maybe in the algorithmic trading space, I have a single algorithm and I want to get a bunch of uncorrelated configurations that all perform reasonably well. You can also have kind of arbitrary constraints within your system. So maybe you have some sort of linear constraint saying, I know the number of hidden layers needs to be less than a certain amount if some other thing is true because it costs too much. And so you can put in that constraint, but then that's kind of an approximation. You may want to actually cut the algorithm off if it takes too much time to train. And so there can be black box constraints as well, where you actually say, this was a failure. Don't search in this region anymore. Kind of learn what's even feasible and then do optimization there. And we can kind of combine all of these different things in interesting ways to solve more than just the number comes in and value comes out type of optimization, and really start to unlock some of the intricacies that are available once you take your data scientists from doing high dimensional optimization in their head and point them at building better metrics and better data and things of that nature. So the high-level takeaway from this is we've built this black box to tune your underlying deep learning and machine learning algorithms. But this really wouldn't have been possible without all of the different services that AWS and EC2 in particular provide. Everything from our evaluation system itself, our optimization system itself, the underlying components of it, the evaluation framework, it's AWS all the way down. And this allows us to service customers around the world, have an SLA that's never been violated, and really perform at our peak by focusing on the software engineering, the platform engineering, the research engineering, et cetera, that distinguishes us from alternatives. And with that, I'll hand it back to Elvis.
Awesome. Cool, thanks, Scott. So, and I love it's turtles, it's AWS all the way down.
Exactly.
Yeah. So, in conclusion, what have we learned today, right? We've learned that AWS has a broad set of compute offerings and AI services to help you get started and to help you scale. And we've learned that SIGOPT has used AWS to build a very interesting and useful product, could potentially save you a lot of money, that allows for easy and efficient and robust optimization of machine learning and deep learning workloads. And personally, I love how you guys are like the Ouroboros, right? You're using your service to improve your service. That's brilliant, right? That's so cool. It's like AI for AI, right? So if you want to learn some more, we've put together a short list of things that might be interesting to you. So in orange are some blog posts, some links to papers, the code that Scott mentioned, a live demo. And in blue, we have some suggested machine learning, deep learning sessions here at reInvent. So things like the Deep Learning Summit, once again, debunking the hype around AI, and a session on reinforcement learning. So we appreciate everyone coming to our session today. Thank you very much. We hope you have an amazing reInvent, and we'll be here in the front to answer questions if you want to come on up after the talk. Thank you very much.
Thank you, everyone.